the substitute hosts. Our host is going to be missing. It's a pleasure today to welcome veteran peers from the talk about XML.
Talk that I gave in this room last May, I think. At the time, I was working on something called Xduce or transduce, which was a tiny language with just two interesting features, maybe even just one interesting feature, these regular expression types. And the point of it was to try to get to build a language with native support for XML processing and static typing. And then this regular expression pattern matching sort of followed in a natural way from the regular expression types. What I'm doing now is trying to carry the results of the transduce project into a mainstream setting by making them available in a full-blown object-oriented language, C#, for example. And what I'm going to talk about today is a preliminary, so this is a big project, and we're not very far along in it, but I want to tell you the motivations, the background, and a design for the core language that incorporates our current understanding of how to combine the XML side of things with the object types of the host language. So there will be quite a bit of technical content in that part of the talk, but it will concern a very small part of the ultimate design. So we'll talk more about what's going to be missing at the end of the talk. Okay, so a little bit of review. The point of the transduce project was taking XML schemas, of which there are many different kinds. There's the XML schema language proper. There's DTDs, the old style ones. There's Relax. There's DSD. There's several other things. So all of these things are type systems in the sense that they're ways of classifying values. But frustratingly, they're not type systems, or they're not used as type systems in the sense that they're not built into programming languages, and they're not used for analyzing the operations on these XML values that programs do. So the point of transduce was to take these things, these schema languages, seriously as types. So what's the point of doing that? Well, obviously, the fact that XML is already typed is a big attraction. It means that the idea of types is already sort of built into the culture of the XML world and is considered a good thing. Another thing that's nice from the point of view of the benefits of static typing in general is that because the types of XML documents are often quite complex, quite refined things, we can expect to get a big bang out of using these things for static analysis. So one kind of obvious point to make is that because these things are complicated, because these tree structures, these XML documents, have complicated types, there's lots of opportunities for getting things wrong in small ways, and it would be nice to have a type checker help with that. But there's a deeper point, and the reason for having this slide at all is, I just want to put this out on the table, is that it's a common observation that making type systems of languages richer increases their usefulness sort of out of all proportion to what you would think you would get. So when people switch from languages with very simple, very weak type systems to languages with stronger, richer type systems, you often hear them come back and say, oh, my programs always work. Once I get them past the type checker, they're always correct. And of course, that can't be true. But it's a lot closer to true than it feels like it really has a right to be. And I call this the curious effectiveness of static typing. So what's going on there? What's going on is that, I was saying over lunch, that a program is this complicated multidimensional thing, but the dimensions are not independent. So if you can, so a flaw in quote, one dimension, a flaw in some design dimension will often show up as a disturbance in other dimensions, e.g., dimensions that can be dimensions whose consistency can be checked by simple static means. So anything to improve the grip of a type system on any aspect of a program will tend to uncover lots of bugs. Okay. So XML, since it should provide a substantial grip, should give you a lot of help in that way. All right, so regular expression types were our formulation of how to get XML schema-like things into a programming language. So regular expression types are a generalization of, I guess you should say, a generalization of a large fragment of DTDs. So they are based on regular tree grammars. They're based on the more powerful form of regular tree grammars than DTDs use. So we use the top-down, non-deterministic formulation of regular tree grammars. Second observation, that the operations needed during type checking, like subtyping, correspond to natural operations on tree automata. However, there's a caveat there. You don't want to implement them in this way. So the correspondence is suggestive. But if you want to really use these things in a type system, you need to do quite a bit of work on making these operations run fast enough on the cases that you're interested in. So a lot of the work that we did in Transduce was on heuristic algorithms for attacking these, in general, exponential problems and getting them to go fast enough on all of the examples that we cared about. Okay, so here's the whole thing. Here's the whole Transduce type system. So Transduce was a first-order functional language, so it didn't even have higher order, didn't have any kind of arrow types. All it had for its types of values were these regular expression types. Regular expression types consist of, well, think of XML documents. So they have strings at the leaf. They have they can be recursive. So a Transduce program consists of this is on the next slide actually. We assume a global set of mutually recursive named type definitions. So this is the backbone of the type system. And those names can appear in types. We have the empty sequence. We have concatenation. We have labeling. Think of these as tags. We also, this is a slight generalization. It's quite easy to do and quite useful. We have a wildcard tag that describes a structure with any tag and a sequence described by T inside. And we have union. And this is full, for the programming language people in the audience, this is full set theoretic non-disjoint union. Okay. And I don't think I want to hammer on this too hard. The point is there are lots of other ways of obtaining the benefits of static typing for XML processing. In particular, there are lots of ways of taking schema languages and embedding them or embedding some part of them into some other type system, like a class hierarchy or the algebraic types of a functional language or whatever. These things are good, but better yet is to take the schema itself as a type, because you then avoid the embedding step and you avoid various kinds of impedance mismatch between the original structures and the types that you're dealing with them as. Right, so we really want to treat these things as first class. Okay, regular expression pattern matching is kind of a free thing that you get once you've understood regular expression types. So regular expression patterns are just regular expression types annotated with variable binders. And what that gives you is a sort of tree grep style pattern match. It leads to we get a programming style that's reminiscent of a lot of the things that are done in XSLT, for example, kind of recursive tree transformer things, and you use this grep for each level of the tree walk. We can use, again, appropriate analogs of these automata theoretic tests for checking standard things like the exhaustiveness and irredundancy of patterns. And a nice observation is that we get all of the nice algebraic data types and algebraic pattern matching of functional languages, ML and friends, just as a special case. And so these patterns are strictly more powerful, more general than ML. This is nice for functional programming people because it's been a project of functional programmers to get these features into mainstream object-oriented languages for a long time. And here they're kind of coming in the design that I'm going to propose, they kind of come in by the back door as a side effect of something else. So that's nice. Our experience in transduce, we haven't written very big programs, but we've written a number of smallish programs. And our experience is that these regular expression patterns are very nice because they allow you to sort of reach into the middle of a quite large and complex structure and grab out the part that you're interested in. Okay, so I said this a minute ago. Regular expression patterns, to be more formal about them, are just regular expression types with one extra construct that says match a value of this type and bind it to a variable with that name. Okay, or to put it a different way, to put it backwards, regular expression types are just patterns without binding. Right, so that's all I'm going to say about transduce per se. What we achieved was to study these basic constructs, understand how to formulate them in a clean way, and we did a lot of work on implementation techniques and making things go fast enough. What we did not do was a full-blown language. It was transduce was a very tiny language. And more importantly, it was a standalone language that was not interested in playing nice with any other language. So that's really the thing that we want to go further with when we take things to the next level. Okay, so the goals of the present project, the Xtatic project, are to take these features, regular expression types and regular expression pattern matching, and to add them to a mainstream, widely used, industrial strength, object-oriented language. There's a stage at which any such project has to choose a particular language, and C# is probably what we're going with. But actually, the technology that I'm describing, most of the language ideas in the rest of the talk are more general than that and could apply to several other languages. The main thing that's important, though, is that the type system of the language be nominal, and I'll come back to that later. That's a requirement that we depend on pretty strongly. Okay, so goals. We want to make this into a very lightweight, kind of smallest possible impact on the existing host language, and kind of source level extension. So we want this to fit very nicely with the existing language, and to be completely compatible at the binary level with existing APIs and existing code. So we want to be able to use all of the libraries of this host language. What that means in particular is that our type system has to understand the host language type system and vice versa to some extent. Right, so that is in one direction completely, in the other direction to some extent. And I'll get into that in more detail. We're assuming no changes to the binary the virtual machine representation of the host language. This is something that one could actually relax, and there could be some benefit to asking for changes in the binary representation. But for present purposes, for purposes of what I'm going to show you today, I'm going to assume that our compilation scheme is going to completely get rid of, at a certain point, all of the extensions that we introduce. And then, finally, we want to make things as simple as possible. Probably what I'm showing you today is simpler than possible. That is, it needs to be extended in some significant ways to really address the problems of real software development. But we're starting off on the simple end, making sure that we fully understand what's going on, and then we'll grow the thing as much as we need to and are able to. So here are the basic ideas. So first of all, the leaves of our XML documents had better be host language strings, in the sense that we want to be able to grab things out of our XML documents and pass them off to arbitrary string handling stuff, and vice versa, get arbitrary strings back and put them into documents. So we want to make the leaves of our tree be host strings. Once we've done that, we might as well allow arbitrary host objects as the leaves of our XML tree. So we've generalized XML a little bit. But this is a very natural sort of for free extension, because we need to do it for strings anyway. So this is one direction. This is how we get host language things into our XML data structures. Conversely, we need to get our things into the type system of the host language, and we do that by augmenting the class types, the ordinary types of C#, with a new set of types, which I'm going to bracket to distinguish them from whatever is there before. And by the way, nothing that I say in this talk is a specific proposal for concrete syntax. So if you don't like these brackets, fine. But for purposes of this talk, I will use these kind of funny brackets to mark XML parts of Xtatic programs. Okay, so the full language is going to be, the types of the full language are going to be the original types of the host language plus new types that look like this. Okay, next, we want to be able to use host language facilities like generic containers, lists and hash tables and whatnot, to store our XML things. So we need to be able to treat XML structures as objects. We do that by introducing a special class type, a new host language type called XML, and introducing this subtype relation that says that any XML structure also has type XML if you want, has the class type XML if you want it to. And obviously, when we come to compiling, we're actually going to smash these together. So we're going to translate all XML types as as instances of the class XML. Next, if we're going to take our XML structures and put them in generic containers, when we get them back out, they're going to have type object, at least until somebody adds generics. So we need to be able to do these standard tricks of getting out things that have type object from someplace and casting them down to some type that we expect them to have. We can do that by extending the downcast mechanism to allow downcasts from XML or object, which is its only supertype, to arbitrary XML types. And those will correspond to runtime tests in just the way that they do with C# downcasts as you have them now, except that, of course, there'll be more complicated runtime tests in principle. And finally, we need to integrate regular expression pattern matching, but that's easy because there's already structure there that supports it nicely. So regular expression pattern matching just gets added into the host language switch statement. Okay, so I mentioned the compilation scheme a second ago. This follows essentially from the requirement that that we not change the CLR. So we need to be able to interoperate with other stuff that doesn't know from XML types, and its view of the world is just classes. Therefore, we conform to its view of the world by smashing everything together into this one type. So when we compile, we first do all of our type checking, report any type errors that we find based on mismatches between these very refined XML types. Then we throw away all of this extra refined type information, replace it all by the single class type XML. Correspondingly, we rewrite all of the XML value constructors in the Xtatic part of the language as data structures that build us instances of the XML class. And finally, we compile pattern matches into host language or binary level switches and conditionals and so on. Actually, I'm not going to talk about this in detail, but just for lack of time, it turns out that if you want to do this seriously, and actually if you want good performance, you'd better do this seriously. If you want to do this seriously, you need to use quite a lot of structure in the target of this compilation of pattern matching. It's harder than just compiling ML pattern matching. So our pattern match compiler actually produces subroutines, and it uses a limited form of exceptions. It uses arrays for keeping track of things. Yes?
After you're done with this compilation, Steve, how do you manage to do the runtime downcasts back to the XML types? Those things are removed, right?
Okay, naively, a downcast says, the naive implementation of a downcast is, here's a static type that I expect that this thing might have, and here's an actual runtime value, and I want to know whether that value has that type. That's actually just a pattern match. So we've got a scheme for doing that. That's the naive implementation, though, and you might, in fact, find that that doing that would be too slow, because doing this pattern match may actually involve walking. In fact, in general, does involve walking over the whole structure. And if the structure is big, then that'll be too expensive to do very often. So we may actually have to cache some information about the type in the structure and have fast paths, things like that. This is something that we haven't thought very much in detail about yet, but probably that kind of tricks will be necessary to make it go fast enough.
So by taking all your types and then bashing them into one CLR level type, it seems at that point that you have various sort of cross-module checking obligations that the CLR can no longer do for you, since you're not willing to hack its signatures. So you're proposing that sort of I have to present my whole program to begin with. And it seems like, you know, given that CLR code is sort of loaded dynamically as needed, I don't see how you. It seems like you could have a completely wrong signature. You know, you load something and it says, yeah, this is XML, and then how are you going to tell?
This is a problem that we don't have a clear view of yet. That is, we have a clear view that it's a problem, and we don't have such a clear view of the solution. We can imagine a range of possible possible approaches. One is you just do things dynamically, so you don't do the cross-module checks except at runtime, or maybe you could manage to do them at link time. Another is perhaps some of this type information that we were just discussing, salting away in the data structures, could be used for doing these checks dynamically but fast. Another is perhaps in some situations you would actually be able to replace the class loader by another one that does understand the XML stuff, and fall back to dynamic checks only as a last resort for when you're running on a legacy.
Obviously, at least at compile time, it seems that you have to have some alternative representation of the signatures for separate compilation.
Yeah. So as long as we're staying, totally inside of the Xtatic world and just compiling a bunch of Xtatic modules, then yes, we need to keep enough information in the compiled forms that we can get it right, do the checks right. Any other questions? Okay. All right. So a very short example, just to give you a tiny flavor of what this might feel like. I've used the wrong kind of brackets in this example. So this is last week's brackets. So read these as bar curly brace brackets. Okay, so here's a very tiny example where we're going to read in an address book and write out a telephone book. And so an address book is, these are declarations of XML types. An address book is has a top-level tag adder book, and then inside it has a arbitrary length sequence of persons, and a person is a tagged sequence containing definitely a name, maybe a telephone number, and arbitrarily many emails, and so on. Then here's how the whole thing looks. So we read in an XML file, and using some built-in facility. What comes back has the maximal XML type. So we don't know anything about its type. It's just, all we know is it's an XML structure. And we then have to cast it down. Essentially, this case statement is a downcast, but I've written it out using the pattern matching notation. Sorry. So we read this in. We do the switch, and we have two cases. The first case handles the one that we're expecting, where we have an address book, and we bind a variable named people to the list of persons inside there. Then we pass the people variable to a method, which I'll show you in a second, called makeTelephoneBook. We bind the result to a variable, and its type is an XML type, and now I've reverted to the new form of brackets. And then we write that out to a file again. And then in this case, so any is the maximal XML type, and we just throw an exception. Yes.
Excuse me. So, are you working on a subset of XML?
We are working on a subset of right. So there's quite a lot of tricky stuff in XML. At the level of values that we don't yet handle. And there's way more tricky stuff at the level of types, particularly in formalisms like schema, that we don't handle. So the question of how much of that we can cover and how much of it you need to cover to be useful is future work.
The question I had specific to this example, I can't tell the difference between like an XML document can have elements and attributes.
I'll get to, I was going to say that at the end, but I'll say it now. So here, we are not handling attributes at all. And this is one of the big theoretical shortcomings of transduce, is that our account of attributes was awful because we couldn't handle anything unordered. We've been experimenting with various ways of getting past that, and we have two proposals. One is to add a general unordered merge operation, an interleave operation to the types at the level of types. That handles all the problems. It's real powerful, but it's actually too powerful, and the algorithms then for subtyping and things like that become too expensive. The other thing is just take attributes as a thing in themselves, and that works fine. That's our plan at the moment for what to do in Xtatic, but I'm not showing it today. Okay, next thing. So here is the makeTelephoneBook thing, and I'm not going to go through all of the details, but the point is that, so here's a more interesting pattern match. I've written this for the sake of the example as a little recursion. So makeTelephoneBook sort of parses off the first person with a telephone number. So this skips over any number of persons not containing a telephone. And then this matches the first person containing a telephone and grabs the telephone and the name. And then uses that to build a new piece of XML structure, which then gets concatenated to the result of calling makeTelephoneBook on the rest of the list of persons. Okay? Yes?
When you use any, if you use any there in the rest, do you, when you from the static type, you actually know it's a persons
Yeah, so
does the compiler optimize
the type checker in the body here will actually realize that rest has type person star. Yeah. Yeah, so writing it as any is a tiny bit of a cheat that we can do because the type checker is actually flowing the information about the type of this through the pattern. Okay. I want to spend the next, in fact, the bulk of the rest of the talk, giving you some details about the core system here. So if we're going to try and understand something in detail, we need to make it really small. And what we've done, the kind of piece of technical work that's finished, is a design for the core language of Xtatic. We call it FX, or featherweight Xtatic. It's based on something called featherweight Java that mainly a student of mine, Atsushi Igarashi, did a few years ago, mainly for the purpose of studying polymorphism and inner classes of Java. So the point of featherweight Java is to be absolutely as small a subset of Java as you could possibly imagine. So small that when you extend it in some significant way, you still have some hope of really fully understanding the result. And I can tell you that if it had been any more complicated, we wouldn't have been able to understand the polymorphic aspect at all. Okay, so we've thrown away everything, almost everything. We don't have all of the standard complicated stuff. We also don't have some stuff that we could perfectly well model, but it would just make the formalization bigger without, in some sense, making it more interesting. And in fact, we even throw away assignment. So let me tell you one slide about that. So, by the way, it was called featherweight Java, but it could just as well have been featherweight C#. At the level of the core language here, they're absolutely identical. So what is this to have a functional, to consider the functional core of Java or C#? Why does that make sense? Well, it's nice to do because it makes everything shorter. But what's interesting is that it's possible to do. So of course, we wouldn't like to program in this language. This is not a proposal for a new functional language. It's just a formalization trick. But the observation is that you can still have something left even if you throw away mutation by doing the following. So you demand that every class be written in precisely a particular form. Namely, every class should have a single constructor. It should take a number of parameters equal to the number of fields of the class, the ones defined here, and also, if it had a superclass, all of its predecessors. So the constructor takes all of the parameters. It initializes all of the instance variables. It does nothing else. And from then on, assignment is forbidden. Right, so what this means is that we can't distinguish an object that we created by saying new to a class with some particular set of values from a different object that we created at some other time by saying new to the same class using the same constructors. We also disallow equality, so there's no issues about identity. So we can then just use the new expression to represent the object. And what that means is that our formalization doesn't need to have a store and store typings and all that kind of stuff. So with that in mind, an FX program is a class table which defines the information that you can read off from the declared classes, plus an expression that we're working on evaluating. The class table tells us a set of names of classes. It tells us the subtyping relation among those classes. And by the way, this is critical that the subtype relation is given to us. So this is what I mean when I say that the type system is nominal. The names of the types are given in advance. and the subclass relation on those type names is given in advance. And then later on, at some point during compilation, we check that the declared one is actually consistent with the bodies of the methods and so on. But the fact that it's declared in advance is going to give us some place to stand in a couple of slides when we're building up the subtype relation for XML things. We need, the class table should also give us a function that tells us what are the types of the fields of each class. And then finally, the class table should have a collection of type declarations for our XML types. So this is the new part. And in particular, we insist that one of the declarations be precisely this. So this is the maximal type, any that I showed you in the example. And the observation here is that we don't actually need to consider it as built in, because here's how you define it. And then you can just check that this one is actually maximal. OK, so the whole type system has three parts. There's the original host language types, which are just these names C. There are the regular expression types, which are all these things, and I'll explain them in a second. And then there's the types of the whole language, which are just the union of these two. And we ensure that the union is disjoint by guarding XML types by these brackets. So in a full Xtatic or FX program, whenever you see a type, it's going to be either C or a guarded T. Okay, then the T's are all of the regular expression types that we saw before, except only we're replacing the strings that we used to have at the leaves by arbitrary host type C. Okay, at the level of values now, we have, again, three kinds of things. We have the original host language values, which are objects. And for purposes of formalization, we're just representing those as new expressions. In a richer language, of course, there would be a store, and then we would have to represent them as pointers to things in the store. That's actually not very complicated to do, but it just sort of doubles the length of everything without making it much more interesting. Okay, so we have these objects. Then we have the XML things. And XML things are sequences of atomic XML things. And atomic XML things are host language values. These are the leaves. And labeled sequences of XML things. And then, again, in the full language, the values are the old original values plus bracketed sequences of XML things. OK, so now I need to tell you about the correspondence between types and values. So we need to know when a particular value has a particular type. And that is very easily defined. So since we have three sets of types, we're going to have three denotation functions. So for the full language, the denotation function is going to take full language values into sets of, full language types into sets of full language values. For the XML part of the language, it's going to take XML types into sequences of XML values. And then for the host language thing, it's going to take us into sets of host language values. So now I'll show you these three things. So this one is easy and obvious. In fact, they're all easy and obvious. But the third one is particularly easy and obvious. It's just sort of the union of the other two, except only that we have to put brackets around the things in the second case. Okay, more interesting. Here's the denotations of XML types. Is there actually anything interesting on here? It's all really simple. The purpose of writing it out is really just to show you that it is simple and to illustrate the design decisions that we made. So, the denotation of a leaf of an XML tree is just the corresponding set of host language values. So this is saying that host values are literally the leaves of XML trees. For type variables, we just unroll the definition. The empty sequence type denotes the singleton set containing just an empty sequence. Labeling just denotes the result of taking the things from T and labeling them with L. If the label is a wildcard, then we get to label it with anything. Concatenation denotes concatenation of the denotation of concatenation is the concatenation of the denotations. And union is just set theoretic union. Right, so that could hardly be any simpler. The host language denotation function is also pretty simple, except we just need to make sure that we throw in all of the XML values. Right? So because recall that the type XML is a supertype of all of these particular bracketed XML types. And we need to ensure that we validate that subtyping law by making sure that all of the XML values actually live in the denotation of the type XML. Similarly, we have to stick them in the denotation of the type object because that's a supertype of XML. Okay. Now, the payoff that we get from the several previous slides is when we come to define the subtype relation of the full FX language, it looks like this. It's totally simple. What this means is that although we have these rather refined, sophisticated regular expression types, in the language definition, what we have to say about when one of those is a subtype of another, when we come to say that, we just put this line. So we don't need any page after page of inference rules or anything like that. We just say, look, you understand what set of documents this XML type stands for. And the denotation functions are just writing that out. And if one of those sets is included in another, then the corresponding types are in the subtype relation and otherwise not. So what's interesting is that you can actually build an algorithm that checks this relation effectively. And that takes work, of course, but you don't show that work to the programmer. Okay. So just a couple of technical comments. This construction is really nice in its simplicity. Why doesn't every language do this? Well, we have two advantages over every language. One is that this language is nominal. Right? So the subtyping relation of C# itself is also very simple because basically the programmer declares it. The programmer does all the hard work of figuring out what should be a subtype of what. The compiler just checks that actually that's okay, and then goes ahead and uses what was declared. So the fact that it can do that arises from the nominal character where you start with the set of names and then you declare the subtyping and then you check it later. So this is important. The other thing is, like C#, FX and Xtatic don't have any contravariant type constructors. Contravariant type constructors would turn our nice, simple denotational semantics on the last couple of slides into something very complicated and technically challenging, right? Because they would mix with the recursive types. So the specialists in the audience know that that would be fun from a certain point of view, but not something that you would want to show to programmers. And the fact that we don't have arrow in the type system, and that when you subtype between classes, you're not allowed to specialize, actually generalize, change the types of arguments to methods, is what makes this true. Okay, we're almost done. So here are the expressions of FX. So we have variables, we have object construction, we have field access, we have message sending, we have regular expression patterns, and just by the way, host language switch statements rolled into one. We have downcast, and we have explicit construction of XML values. Those XML values are bracketed sequences of either labeled subsequences or expressions, right, other expressions. And now we need to do something a little bit, I have to show you one subtlety that's important for making it all kind of smooth. When expressions appear in these sequences, they might be either leaves or subsequences that we want to splice in. And we have to actually treat both of them in a syntactically uniform way. So here's the example. Suppose that the variable x in the surrounding context is bound to a host string. And suppose that the variable y is bound to some XML sequence, some XML value. We want to be able to write something like this. So we're constructing a value which is tagged entry, and the sequence inside the tag consists of the sequence described by y and then one more element, which is a tagged string. So the tricky thing here is this comma means append just because the thing on the left is a sequence. But if it had been, if we had put x there, we wouldn't mean append. We would mean cons. Fortunately, there's a simple, well, there are two ways to deal with that. One is to somehow mark these occurrences of variables by saying, you know, this one I mean you should splice it in, and this one you should include verbatim. That would be horrible, right? That the anti-quotation languages with anti-quotation get away with it, and people can bear to program in them as long as it's not used too much. But this would be used all over the place. So we really don't want any kind of special anti-quotation syntax. Instead, we just ask the type checker to work it out. So comma just means append if the things on both sides have XML types, or cons if they have host language types. And this rigid distinction, this rigid separation between the host language types and the XML types is exactly what allows us to do this. Once we have done that, we get another benefit for free, which is there's a similar confusion in pattern matching. So suppose that we have a pattern that looks like this. So the pattern is matching a single string. Now, is this a host language string? That is, should x be bound to a host? Should its type be string in the body of the case? Or is this a singleton XML sequence containing a string object? Right? It matters because they're represented differently. And you might want both. You could imagine wanting both. Fortunately, once we've established the convention on the previous slide, there's no reason to want both, because you might just as well always choose the second. So if this pattern corresponds to a host language type, then so if it's just a singleton host language thing, then you might as well just extract that singleton and bind its host language type to the variable. Because when you use that variable in the body of the case, it's going to be for purposes of constructing a new XML value. And at that point, the type checker will realize, oh, here's a singleton host language thing that needs to be consed in rather than appending.
I'm a little confused about the power of this. Suppose I had a pattern that was any x, comma, some complicated expression, comma, any y. Will it search the whole list?
Yes.
So, and it'll just pick the first one it finds?
That's the intention. There are different variations, and we're actually not sure ourselves yet which one is best. You might like to have a non-ambiguous version where you're sure that each pattern can only match a given value in a single way. There is some of our pragmatic experience with programming suggests that might actually be better. So then the answer to your question would be no. But from the point of view of the rest of the language design decisions that we're making here, it could go either way. Another thing that we might want to play with is rather than just getting a single binding, we might want to get back all the bindings. That is something that we haven't explored in this design, but that one should explore, because that kind of stuff is very often useful. Okay, so I think it's time to wrap up. So what's the current status? So the definition of fx that I showed you that I sketched on the previous slides has just about converged. We're still tweaking it, but the tweaks get smaller and smaller. We have a prototype interpreter for that language that runs and can execute some small programs. The main so that kind of that's a front-end prototype. We also have a back-end prototype of the main back-end technology that's going to be needed to make Xtatic as a whole usable, and that is pattern matching. So we expect and hope that these regular expression pattern matches will be absolutely ubiquitous in XML-intensive parts of Xtatic programs. That means that they have to go like lightning, and that means that you have to work hard on compiling them. You might hope that all of the technology for compiling ML-style algebraic patterns would apply in this case, and it does to some extent, but it's not enough because, in particular, our patterns are recursive. Right? So our patterns are these arbitrary size, in general, infinite regular trees described by finite systems of equations. ML-style patterns are all finite depth. And that means that the automata theoretic compilation tricks that have been developed in high-performance ML compilers tend to diverge when you apply them to our patterns. So you need to do something else. And one of my students has maybe it's hard to know, but maybe 2/3 finished proposal for how to do that. The next thing we're going to need is a runtime system, and that's the part that we're just starting on. And I also mentioned the extension with attributes. The main point about the runtime system is how do you represent these XML structures? What's the runtime data structure that you use for representing XML trees? There's one obvious choice, which is DOM, which I think probably we agree and people generally seem to think would be the wrong choice. DOM is a very general, very flexible, and rather heavy and slow and expensive thing. So we need something lighter weight. The question of exactly how it should interoperate with existing things is still open. So there are various lightweight versions of DOM. We might be able to use one of those. We might be able to implement our own lightweight version of DOM. We might be able to implement something yet lighter weight and translate dynamically, et cetera. So this is something we're just thinking about. Okay, as I said at the beginning, the part that we've done is in reasonably solid shape, we think, but there's plenty left to do. There are really a lot of things left to do. I just mentioned the runtime representation thing, and I mentioned a few minutes ago the need to explore other styles of pattern matching, other primitives for pattern matching. There are lots of them out there, and we believe that many of the ones that are out there will fit into the typed framework that we're playing with. In particular, we've noticed that big parts of, more than you would think, of XPath can be translated into our regular expression patterns. So, but we really haven't carried that exploration very far. Yes?
Is there a simple translation of what's it called, the // the find this pattern arbitrarily deep?
Yes.
Do I have to write a little function off to the side that does the traversal, or do you have an operator that...
Hang on a second, let me page it in. No, it involves the wildcard tag. So these patterns are general regular expression types. So you can write a recursion. Let's see, you can write a pattern that says either it's the thing that we're looking for, or it's anything followed by the thing that we're looking for, or it's any label dominating the same. Okay, another whole big area that we haven't considered essentially at all yet is what about updating these XML structures? So we've focused our attention on a style of XML programming where you load in one XML tree, you examine it, and in the course of examining it, you construct another one. So you're doing sort of tree transducing rather than manipulating structures in place. That's fine for many applications, but for many applications not. You need to update in place. And the question is, can we adapt or generalize our type system to handle those cases as well? There are various possible approaches. We haven't explored any of them in depth. One is that we could leave the type system alone, just add in update operations, and let it be statically unsound. I got this idea from Wolfram a few minutes ago, actually. And then use runtime checks, just as one does with array updates, to maintain safety. Another thing one could do is add essentially mutable types to the type system. That would, of course, decrease the flexibility of the subtype relation for the mutable structures. And we would have to understand how the mutable and immutable parts of the world would play with each other. Then there are lots, as I said a little while ago, there are lots of other features besides attributes, features of XML that need to be considered in this framework. So namespaces is one. There are a whole bunch of other ones. And I said we'd like to. It probably isn't possible or even desirable to get all the way to the power of something like XML schema in a type system. It would make the kind of analysis that you would have to do in your programs too complicated. On the other hand, since schema is out there and people like it and are using it, we want to get as much of it as we sort of sensibly and cleanly can. And exactly where that dividing line is not clear yet. Yes?
I understand the part about namespaces. Do you have any idea, like, exactly what aspects of XML you're sure you're going to support besides, well, right now you have, I assume, element nodes and so on, and you're working on attributes. Besides namespaces, like, are you familiar with the XML info set? Are you going to support that?
We don't know. Yeah, that's on the list of question marks. With a lot of these things, for example, with namespaces, it feels like really just a matter of work to get it in, that there won't be any fundamental, horrible conceptual problems. It'll just be a matter of sort of unifying the syntactic conventions and things like that. But there can always be hidden gotchas. And we definitely know that with things like schema and XPath, there are parts of those proposals that are quite complicated. We probably can't get all the way. Okay. Quickly, integration with polymorphism. Not important now because polymorphism isn't there yet in C# or the other sorts of host languages that we're interested in. But it may come in those languages, and when it does, so we'll be interested in integrating with it. And there are definitely some theoretical problems there. So that's a big area. Another one that we really haven't thought about at all, except to recognize that it's a serious problem, is what to do about XML structures that are too large to store in memory. Right? You need to address those things in different ways. You get them as streams rather than as trees, and that difference probably has to be reflected in the type system as well. We don't have a proposal for doing that, but I'm putting it on the slide just to show that we recognize that it's important. Okay, I'm going to blip past the related work with apologies to present company and others. Here are the people that are working on Xtatic, both at Penn and elsewhere. And here's the URL, and that must mean it's the end of the talk.
So I think your title slide said that this was static XML typing in C#. It seems to me as it's really playing nice with C#.
Yeah. Yeah, that's right.
Because all these types get smashed into XML or what you call like big X, little f, little f. By the time C# sees it. Is there any hope for doing something like this? I mean, it doesn't have to be C# in any existing language that wasn't anticipating XML coming along, whether it's Java or C#. Could you add this kind of stuff to it, or would it just be a monstrous amount of work?
Well, so ultimately, if the Xtatic design turned out really nice, and if we put a huge amount of work into the engineering of the implementation and made our compiler just as good at the C# subset as somebody's C# compiler, then we could just rename Xtatic to C#. And then it really would be native XML processing in C#. That's a kind of question of definition, but the intention is to leave that path open. And in any case, even if you don't go all the way down that path, to make Xtatic look so much like C# that C# programmers find it completely natural and just write their. So you can take a C# programmer, tell them about 2 more constructs, and give them a copy of the Xtatic compiler instead of the C# compiler, and they're off and running. That's the intention. Yes.
So what are the usage scenarios you have for Xtatic? Like, who do you expect to use Xtatic?
The set of users that we know, that we're pretty sure would be happy with it, are people that are using XSLT now, because those are the kinds of applications that we've tried in Transduce. Whether it can go further, and whether people that are more interested in databasey kinds of applications would be happy here, I think still remains to be seen. And in particular, there are questions about the primitives that we provide for querying, because database people expect to have much richer sets of query primitives and be able to grab a whole bunch of things out at the same time and treat them as treat the collection as a unit, and so on. So that dimension needs to be pushed.
One more question. XML documents, I guess this goes back to what you support, and I have certain out-of-band data, like processing instructions, comments, stuff like that. I'm not going to those words. I'm not sure. Do you see any importance in being able to support that in Xtatic?
Probably, and how to do it is again on the list of question marks. Another thing on the list of question marks is ID refs.
Quotation and anti-quotation, stuff like that. And I was wondering, your patterns seem structural, but one of the things people use, what is it, XPath or whatever for, is, they hardwire some constant in there. They say, I want to find all the fields where the name is Fred. Do your patterns include that capability?
So there's a foundational question and a concrete syntax question. At the foundational level, the power of our patterns is such that we can express that. At the concrete syntax level, we don't know how to write it nicely in a way that interacts well with the rest of our pattern match syntax. So in fact, at the source language level, we don't support it at the moment, but we'd like to. Maybe we should take further questions offline?
Thank you.
Okay, thanks for coming.